Okay, so today we are going to be going over the 2008 AP Physics C Mechanics free response question number 1. So as you can see in this problem, there's a skier on a slope, and as a preview to this problem, it's going to involve a differential equation, which is an equation that contains a variable and the derivative of that variable, and we will get to that as we go through this. So, a skier of mass m is skiing down a frictionless hill that makes an angle theta with the horizontal, as shown in the diagram right here. The skier starts from rest at time t equals 0 and is subject to a velocity-dependent drag force due to air resistance in the form F equals negative bv, where v is the velocity of the skier and b is a positive constant. Express all algebraic answers in terms of m, b, theta, and fundamental constants. So part A, on the dot below that represents the skier, draw a free body diagram indicating and labeling all the forces that act on the skier while the skier descends the hill. So let's think about what forces are going to be acting on the skier as he goes down the hill. Well, as an easy one, there's going to be the weight, and that equals, I believe, the skier, his mass, capital M, so weight equals mg. And let's also think there's going to be a normal force, isn't there? Because normal means perpendicular. Normal force is always perpendicular to the surface. And so there's going to be a normal force, not straight upward, but because the surface is on this angle, it's going to come out like this. And so we're going to label that N, and that's going to be our normal force. And our last force, because it's a ski slope, there isn't going to be any friction involved, but it does tell us that there's this velocity-dependent drag force. And so if we call basically this the positive direction, it says F equals negative B, that's the drag force. If we put it in this direction, that's just going to be F equals B V. And so those are all of the forces acting on the skier. I'm just going to draw this. You aren't required to, but so it makes more sense later, our theta and the angle at which the slope is at. And so that's all of part A. That's all you have to do. Part B, write a differential equation that can be used to solve for the velocity of the skier as a function of time. So to do this, we're going to start by thinking, how can we write this differential equation? And like I said, a differential equation is an equation that contains a variable and the derivative of that variable. It's a simple explanation, but one way we can think about this is that we're going to want to get velocity, so time and velocity related, and we want to get velocity and the derivative of velocity with respect to time. And that's the variable and the derivative of that variable that we're going to want to get. And so how we can start thinking about this is we can do the sum of forces in the x direction equals mass times acceleration in the x direction. And if we look back at our image, we're going to tilt our axes a bit and say this is the x-axis and this is the y-axis. So it's on a bit of an angle, but that we tilt them so that it's easier to get these values. And so one way we can think about this is A is equal to dv over dt, right? Because acceleration is the derivative of velocity with respect to time. And so what we need to now do is figure out what forces are involved in the x direction, because we're going to be summing our forces in the x direction. And so in order to do that, I'm going to draw a new free body diagram so that I can expand it and better see the forces involved. And so I actually paused the recording and redrew the free body diagram right here. And I also added this indicator for the direction of the acceleration. And so when we look at this, what I did, and I explained this earlier, is I redrew the axes so that they're like this now and they're tilted that way. And now the x-axis goes along this way, y-axis goes along that way. And the reason I did that is so that the normal force and the drag force BV are along the axes, and that will make it easier for us to actually use those values. However, in doing so, the weight mg is no longer along either of the axes. And so what that means is force is a vector, and that means that there are components, and we need to solve for those components in order to actually use the weight mg in equations. And so when we look at this free body diagram, we're going to use trigonometry to do that because there's lots of triangles within this diagram. And so what I can do is I can take this down and extend the y-axis and form a right triangle right here. And so when we look at this, we have this triangle right here, that angle, and then we also have the triangle right here, which is a right triangle. There's the 90-degree angle, but there's also this one here. And so what we have to know is that right here, there's a 90-degree angle right there. And so that means that this and that have to add up to 90 degrees, those two angles. Well, within this triangle, theta and this angle right there have to equal 90. Therefore, because this and that have to equal 90, and this and that equal 92, this angle right here must be theta. And so now that we have theta, we can use that to solve for a variable. So let's, one thing to also know is that mg is the hypotenuse of this triangle right there. And so we want to get our horizontal and vertical components. This is our horizontal component. This is our vertical component. So let's think of how would we solve for those? Well, let's just use sine and cosine to solve for those. And so if we're using that angle theta right here, that means that sine of theta is going to be equal, and let's call this mgh for, no, let's just call it h for the horizontal component. That's going to have to equal h over mg. Well, a horizontal component is then going to be mg sine theta if we're solving for a horizontal component h. We can do the same idea to solve for the vertical component, and we can say cosine of theta, adjacent over hypotenuse, has to equal, and we'll call the vertical component v over mg. Well, for solving for v just equals mg cosine of theta. So there we've just solved for our horizontal and vertical components. Now we can actually use those in a meaningful way in our equations. So, like I said earlier, we're going to have to sum our forces in the x direction, but now we have those forces and we can actually do that. And so let's go back to the diagram and see which forces are in the x direction. The x direction being this. And so what we're looking at here is that our mg sine of theta, this right here, is going to the right of that dot if we look at it. So if we're calling the right side or this direction positive and this direction negative, when we sum our forces in the x direction, and so if we bring our equation over here, we have that if we sum our forces, we have mg sine of theta, that horizontal component of the weight, minus bv, because that's going in the negative x direction, has to equal m capital M A x, because the mass of the skier is capital M. Well, like we said earlier, acceleration is dv over dt. A equals dv over dt. So we can rewrite this and say mg sine of theta, minus bv has to equal m dv over dt. And I just multiply dv over dt times m. And so that's our differential equation. Remember I said earlier, a differential equation has the variable and the derivative of that variable. We have our variable and then the derivative of that variable. And so there is your differential equation. And so for part C, it says determine an expression for the terminal velocity vt of the skier. Well, what we're going to do is we're going to take this equation and I'm going to copy and paste it over to another page. And we are going to use that to figure out our terminal velocity of the skier. And so mg sine of theta minus bv equals m dv over dt. Well, whenever we hit terminal velocity, right, that's the maximum velocity that the skier will reach. That's the highest velocity it will reach. Once it hits that, the velocity is not going to be changing. That's its maximum velocity. That's why it's called terminal velocity. Well, at that terminal velocity, if the velocity isn't changing, that means the skier is not accelerating. Therefore, the acceleration is the acceleration is 0. And so what we get is mg sine theta minus bv has to equal 0 because dv over dt, that's equal to a, and a equals 0. And so actually I'm going to call this vt for terminal velocity. So I'm adding a little subscript t right there. Well, if we solve and we want to isolate vt, we're going to add b vt to both sides. And when we do that, we are going to get b vt equals mg sine of theta. And it's just a matter of simply dividing by b on both sides. And when we do that, we get vt, or terminal velocity, equals mg sine of theta over b. And there is your terminal velocity, the answer to part C. Now let's go back and look at part D. Solve the differential equation in part B to determine the velocity of the skier as a function of time. Now this is a very complicated step of this problem, part D. And in order to do so, it's going to involve some integration. And in order to start, what we're going to first do is kind of set up like we did earlier. Or actually, we can use the same principle. So we said a equals dv over dt, and sum of our forces in the x direction equals ma, and the acceleration being in the x direction. And so when we did that, what we got was this equation right here. And I'm going to copy that again over and paste it right here. Well, one thing that we want to do from this is we want to isolate dt, and we want to get dt on its own on one side. And so in order to do so, we can just multiply by dt on both sides, and then divide by mg sine theta minus bv from both sides. And you're probably all, if you're doing this problem, you understand some pretty basic algebra. And when we do that, we're going to get dt, so I'm going to redraw that, dt equals mdv over mg sine theta minus bv. We're treating this basically this side as one whole thing, and that's why we can divide by that and bring it over to the other side. And so now that we have this equation, we're going to want to integrate both sides of it. And so what we're going to do with dt is we're going to integrate that from 0 to t, and on the left, we're going to integrate from 0 to v. And same things, mdv over mg sine of theta minus bv. And so one thing that you'll notice, and if you know calculus, is that this bottom part we cannot simply integrate. We have we have v here, which is the variable that we are integrating with respect to. But we cannot simply do that. We need to use u sub. And so what we're going to do is we're going to call u, that's going to equal mg sine theta minus bv. And so if we take the derivative of u with respect to v, we're just going to get negative b. And so we can rearrange this so that we can solve for dv, and we get dv equals du over negative b. And so when we go back to our equation above, we go 0 to t, dt is going to be equal to m over u, because we replaced that with u, times du over negative b. And so let's rearrange this a bit, and also we can simply integrate this left side and just say t equals m over negative b times du over u. And that is from 0 to v. Now, one thing I'm also going to do is I'm going to replace our limits. All right, so let's say we're going to do u at 0. Let's go back to the equation. We said u is mg sine theta minus bv. If v equals 0, that means that we simply have mg sine of theta minus b times 0. So that's just going to equal mg sine of theta. And if we do v equals v instead of v equals 0, v equals v, we simply get mg sine theta minus b v. And so let's rewrite that and say t equals the integral, and that's from mg sine theta and mg sine theta minus b v of, and actually, let's do another step. Let's pull out, because that m over negative b, or negative m over b, is just a constant. Let's pull it out, and now we have du over u in the integral. Well, du over u, that's just going to be the natural log of u. Okay, so we have negative m over b times ln of u evaluated at our limits. So mg sine theta and mg sine theta minus b v. Another thing that we should do is let's move this onto that side, the negative m over b. And so when we do that, we're going to get negative tb over m. It's going to equal to the natural log of u evaluated at mg sine theta minus bv and mg sine of theta. And so when we do this, we're just going to simply evaluate u at those, and I'm going to take this up to the top here. Up here, and we have negative tb over m has to equal the natural log of, and that's going to be, it's going to be the natural log of mg sine theta minus bv minus mg sine of theta, or minus the natural log of mg sine of theta. If you know your log rules, whenever the log has the same base, so natural log of a number minus the natural log of another number, that's going to be those two numbers divided by each other. And so what we're going to get is the natural log of mg sine theta minus bv over mg sine of theta. And so the next step, which you might be able to tell, is we're going to raise e to each side. And so that'll bring down the natural log. And so when we do that, we get e to the negative tb over m has to equal e to the natural log of, something. That's just going to cancel the e and the natural log out. And so like that, And so that's going to bring down so that we just have mg sine of theta minus bv over mg sine of theta. And so finally, what we're going to do is we're going to multiply mg sine of theta by both sides to, isolate mg sine of theta minus bv. And so when we do that, we get mg sine theta e to the negative tb over m has to equal mg sine theta minus bv. Now, another thing that we can do is we can subtract mg sine of theta from both sides, so that we get negative bv on one side. So mg sine of theta e to the negative tb over m minus mg sine of theta has to equal negative bv. We're going to multiply by negative 1 so that we make this positive on both sides. And what we're going to get is mg sine of theta mg sine of theta minus mg sine of theta e to the negative tb over m has to equal bv. The last thing that we're going to do is divide by b, and we're also going to factor out an mg sine of theta because it's in both terms. And so next we're going to divide by b, and so when we do that, we're going to get v equals, and I'm going to factor out that mg sine of theta, so I can say mg sine of theta over b, because I divided by b, times 1 minus e to the negative tb over m. That right there, that is your answer to part D. That is your answer to part D. And so, on to our last part, the final part, which says, actually it's not on here, but the second part, which I have on another sheet, is on the axes below, sketch a graph of the acceleration a of the skier as a function of time t and indicate the initial value of a. Take downhill as positive. And so this problem, it gives us a graph like this, and it says, here's the origin. This axis is a, this one is t. It has the arrows. And so we're basically going to draw what happens to the acceleration. Well, this is a terminal velocity problem, and so with terminal velocity, the acceleration is going to approach zero. It's going to approach zero. So if we think about it mathematically, let's go back to the equation where we summed our forces. So the sum of forces in the x direction equals ma x. Well, we said that the sum of forces in the x direction were mg sine of theta minus bv has to equal to ma. And we'll do a aught because that's going to be, it says it wants us to indicate the initial value of a. That's a with the little subscript 0 is our initial value of a. Well, at t equals 0, which would be our initial value of a, there's not going to be a drag force on here. So this value, the value of the drag force is going to be 0. So what we get is mg sine of theta equals ma aught. Well, what we can do now is we can see that there's an a on both sides. So we can there's an m on both sides. So we can divide the m out and say that a aught equals g sine of theta. So that's our initial value there. And so when we look back at the graph and think about what the acceleration would look like graphically, we can think that the velocity is going to approach a maximum value throughout as the time goes on. The velocity will increase, but that increase in the velocity will start to decrease as time goes on and it'll reach a maximum. So the velocity is going to look something like that. And there's the terminal velocity. However, that means that the acceleration is going to decrease and approach 0. So the acceleration is going to look like that because, like I said, the velocity is going to, acceleration is the derivative of velocity, and so that change is going to get a lot less as we go along, and that change in the velocity is going to be much, much smaller, and it's going to approach 0 when the velocity is constant, essentially, terminal velocity. And so there's your graph of the acceleration, and that is your part E to this problem.